Welcome students to Pradeep sir classes as PSC, and today we are going to solve that particular numericals that is based on principle of Bowman's, and is for today's class it is very interesting and more conceptual, and we show that the when a meter rule is imbalanced, or where the rule, that particular rule is light or it is heavier, and if it is heavier, then where we can put that particular weight and where that particular weight of the meter rule acts. This is at the center or gravity or another point. And what are the different types of balanced? And the last numericals is more conceptual, that is used in today's and everyday paper waiters can cheat you. And so let's take your copy and pen and let's enjoy all the numericals. So thank you, and please subscribe if you think that it is more conceptual. Okay, let's say student welcome, and starts with that particular the next step. uh, the question 8 is completed in the previous classes, so if you not see, then go to the uh, first and the different classes and note down. And today is the most, I discuss with the most important part, that is the numericals. All the numericals are related with the meter rule, and the question number 9 is a very important question number 9, and it is more conceptual also. So uniform meter rule balances horizontally on a knife edge placed at 58 centimeter mark. So uniform meter rule, what is uniform rule? That is the uniform means for that particular meter rule, uniform definition is there is the same materials or properties. So this is, if we say this is a meter rule, this is a meter rule, suppose it is a meter rule, it is a meter rule. So uniform means mass distribution is same, mass distribution. Suppose it is in that particular portion is sink and this particular portion is bulged out, and this is not, the meter rule is totally uniform, that is called uniform meter rule. And suppose it is at zero, sorry, it is at 0 mark, and this is 100 centimeter, and this is I think, and you can relatively, this is 50 centimeter, suppose 50 centimeter. Okay. So the question is a uniform meter rule balances horizontally on a knife edge placed at 50 centimeter mark. So 50 centimeter mark, suppose this will be the 50, so there is a knife edge here, and this is 58 centimeter mark, 58 centimeter mark. Yes, then 58 centimeter mark, when a weight of 20 gram force is suspended from one end, it remains horizontal when a 20 gram force is suspended. Suppose I want to balance this pen at this one, at that particular position. So this particular position is the midpoint. But if we balances that particular pen at that particular point, then we must place a weight along that particular end. So this particular end is very small. So that is the main point, and concepts hide here. Okay, so you have to determine first the shortest portion. So this portion is the small distance, and this will be the greater distance compared to that particular meter rule. So this is the smallest edge, so here you have to place a weight of 20 gram force. 20 gram force. And the first part of this concepts is draw a diagram of the arrangement. So the first one is completed, and then what is the weight of the rule? What is the weight of the rule? So you have to calculate the weight of that particular rule. At that position, the this meter rule is in equilibrium. So the concept is the next where is the center of gravity of that particular meter? You can say easily it is at 50 centimeters. Yes. So this is the center of gravity. So we know that here acts the weight of the meter rule. So weight means mg, or if we convert this into a gravitational unit, then we can write m gram. Suppose if this is m gram, mg is not equal to m gram. Mg means weight. So weight acts along the center of gravity. But let us consider the weight of the meter rule. Suppose mass of the meter rule. Okay, mass of the meter rule is m gram. So mass of the meter rule is m gram. So m gram force act along that particular direction, m gram force. And then from the principle of moments, we can say that this is the knife edge. So this particular force can act along clockwise direction, so this is clockwise moment. So clockwise moment equal to 20 gram force into so this is 58 centimeters. So 100 minus 58 centimeter. So 100 minus 58 centimeter. This is the distance. This is centimeter. So this is clockwise moment, and clockwise moment is always taken as negative. So this is negative of 20 gram force into 100 minus 58 centimeter. And you go to the next part, anti-clockwise moment. Anti-clockwise moment. So anti-clockwise moment is taken as positive. This is the convention. So anti-clockwise moment, that is this force acts along that particular direction and it brings back to the equilibrium. And if that particular two moments are equal, so from principle of moments, we know that clockwise moments is equal to the anti-clockwise moment. That's why the meter rule is in equilibrium. So anti-clockwise moment equal to plus of m gram force. This is the weight into perpendicular distance. So this is the distance. So this is 58 minus, and this one is 50 centimeters. So 58 minus 50 centimeters. This is the distance. So clockwise moments in equilibrium condition. So from principle of moments, we can write that from principle of moment, we can write clockwise moment, that is 20 gram force into 100 minus 58 centimeter. This is equal to m gram force into 58 minus 50 centimeter. Okay, so 20 into 100 minus 58, 8 or 2, this is 2 and 6 and 4, 42. Yes, 42. Then this is equal to m into 58, that is 8. So m equal to, that implies m equal to 20 into 42 by 8. So 4 5s are 20 and 4 2s are 8 and 2 2s are 4, 2 1s. So 5 1s are 5 and 10. Oh yes, 105. What is the unit? Obviously this is gram force, gram, this is gram, m equals to gram, and if we uh, write in terms of weight, then we can say that 5105 gram force, it is the gravitational unit. So 105 gram force is required to balance the meter rule. Okay, so this is the concepts of meter rule, and the main concept is you have to think that the force means the average total force or weight of the meter rule acts at yes, it is 50 centimeter, since this is the meter rule. So that is the main concept. All the numericals related with that concepts. Weight of the meter rule acts at the center of gravity. So question number 10, if we go to the question number 10, this is the diagram below shows a uniform bar. This is uniform bar. So this is a uniform bar. This is 0 mark. So if we take that 0, then 0, 10, 20, 30, 40, 50, 50, then 60, 70, 80, 90 and 100 centimeters. So it is a meter rule, and shows a uniform bar suspended at the midpoint and a weight of 40 gram force. 40 gram force is placed at a 40 centimeter mark to the left of this O, and this is the left portion. And how can we balance the bar with a weight of 80 gram force? So 80 gram force, if this is in place of, if this is 40 gram force, then simply you can say that it is kept on the 40, but this is a greater amount of force, so you have to place it in a small distance so that it can equilibrium. So suppose we can place 80 gram force at suppose 20 centimeter. Then clockwise moments equal to 80 into, this is 10, this is 10. Let's do this numericals. Question number 10. It is so simple. And this is a meter rule, and here it is given that this is a O point and this is a knife edge, and this is, I think this is 20 centimeters. Suppose x centimeter. Suppose x centimeter. This is the distance, and here we placed 80 gram force. Okay, and there is another at 40 centimeter. At 40 centimeter, there is a mass of 40 gram force. So this is the clockwise moment, and this is anti-clockwise moment, and the clockwise moment is 80 into x. The clockwise moment is 80 into x, and this is equal to 40 into 40. So x equal to 40 into 40 by 80, and 2 and 2 20. So the answer is 20 centimeter. So you have to place 80 gram force in 20 by balancing the weight of this one as 20 centimeter to the right of the point 2. Okay students, so it is simple, and all the meter rule concepts, and this is the main concepts. So clockwise moment is taken, I repeat and hammering you again and again, the clockwise moment is taken as negative, and the anti-clockwise is taken as positive. Okay, students. So go to the next questions. Question number 11. So question number 11 is figure 1.37. There is a figure, yes, and that this is 50, so this is 0 and 100, so it is a meter rule, and knife edge is at 50 centimeter, and there is a mass of 40 gram force at this one, and if 40 gram force is this one, then it is balanced, but here it is a 20 gram force. So that particular force is greater than that, and it rotates in anti-clockwise direction, rotates in anti-clockwise direction. But the question is, the figure is this shows a uniform meter rule placed on the fulcrum, and it is O, and having a weight of 40 gram force at 10 centimeter mark and a weight of 20 at 90 centimeter mark. Yes, and is the meter rule is in equilibrium? Is the meter rule is equilibrium? No, because if this is 40 gram force and we can apply this is also 40 gram force, then the particular meter rule is balanced. But here it is not balanced, because this weight is less amount of this, and this is half. So the first part, the answer is no, it is not remain in equilibrium. If not, how will the rule turn? How will it is in anti-clockwise? So no, the rule will be turned in anti-clockwise. It is clear, since this mass is greater. Oh yes, and then, and if not, how will the rule turn? The next one is, how can the rule be brought in equilibrium? So this is the main point. And think, students, if we plus a mass of suppose m gram at particular positions from the fulcrum, let's then it will be in equilibrium. So this is the meter rule, and this is at 50 centimeter, and here at this 90 centimeter there is a mass, and this is 20 gram force, and this from that particular direction point it is 10, 20, 30, 40. It is 10, 20, 30, 40. So this is 40 centimeter, and here is also a mass of this gram force, 40 gram force, and the distance is 10, then 20, then 30, then 40. So it is a total is 50 centimeter, so it is 40 centimeter. It is also 40 centimeter, so it is also 40 centimeter from that particular position. So this is not balanced, and this is in anti-clockwise rotation, so we have to plus a mass of suppose m gram here, and it is the distance from this and this one, from this and this one is suppose x, from that particular position to this one is x. So this is the clockwise, so clockwise moment equal to x centimeter into x centimeter into how can the rule be brought in equilibrium? By using an additional weight of 40 gram force. So the question is 40 gram, we can, oh, this is 40 gram, sorry, this is 40 gram force. How can you apply, but takes the meter rule into equilibrium with the applications of 40 gram force? So this is 40 gram, so x into 40, x into 40 plus x into 40 plus x into 40 plus 20 plus 40 centimeter, so 20 plus 40, this is the clockwise moment, 20 into 40, this is the clockwise moment, and the anti-clockwise moment is 40 into 40, and the clockwise, and this is, so this is equal to 40 into 40. So this is equal to 40 into 40. So x equal to, we can write that x equal to 40 into 40 by 40 into 40 divided by, extremely sorry, 40x. This is so simple. 40 into 40 minus 20 into 40, 800. So 16 minus 800. So x equal to 0 0 by 40. So this cancel this one. So 4 2 ja. So this is 20 centimeter. X equal to 20 centimeter. So x equal to 20 centimeter. 20 centimeter. So x equal to 20 centimeter. Where this is the fulcrum, this is at 50 centimeter. So at that particular position, so this is 20 centimeter. 20 or 50, that is 70 centimeter from zero position. From zero position, this is zero position. So you can write here that 70 centimeter from 70 centimeter from 0 centimeter mark. Yes, so this is clear. So the question number 10 11 question number 11, this is 40. So all the numericals are somehow related with clock and anti-clockwise moments, and some of it is used at if the meter rule is weightless, there is very light meter rule, then the weight is particularly acts on the center of gravity, that is 50 centimeter. It is not taken into account. But if the meter rule is heavy weighted, then the mass acts at that particular position, that is at 50 centimeter. So next question is question number 12. Question number 12. When a body weighs 20 kg force sits at one end of 4-meter long seesaw, so it is 4-meter long seesaw, it gets depressed at this end. How can it be brought to the horizontal position by a man weighing 40 kg? So it is so simple numericals. So this is a meter rule. This is a meter rule. And this is a meter rule, and it is 4 meters. So this is 0 and this is 4 meter. So this is 2 meter. There is the fulcrum. 2 meters. It is 2 meter. So 4 meter. When a boy of weighing 20 kg force sits at one end at 4 meter, so a body weighing at that particular position, and this is 20 kg force sits at one end, it depressed along this direction, so clockwise moments acts. And if we place a particular position at that particular position, and we take that this is x centimeter, so at that particular position there is a weight of 40 kg force, and if 20 kg force is placed at that particular position, then it is equilibrium. But since it is 40 kg force, so the distance must be less than amount of 2 meter. So this is the clockwise moment. The clockwise moment is 20 into 20 kg force into 2 meter, and this is equal to 40 kg force into x meter. So x equal to 40 by 40. So this is 1 meter. So from the fulcrum it is 1 meter, so this portion is also 1 meter. So we can say that from one end it is 1 meter, or from the fulcrum it is also 1 meter. So this is the answer. So it is so simple questions, and it is related with, and by sitting a distance of 1 meter from the center of the side of the opposite side. So I think students, you think that this channel is too much conceptual, and all the numericals are I clear your views so sincerely, and I think that you can imagine that particular concepts, as well as the as well as when we read that particular figures, and we know that this is an imaginations that can if we draw the particular figures and then we solve that particular, that is figure and numericals, and then we uh, I think clear your concepts more better. So if you think that this channel is wow, it is more conceptual, then please subscribe. So the next questions, I go to the next questions. Mm, a physical balance has its arm of length 60 centimeter and 40 centimeter. A physical balance has its arm of length 60 centimeter and 40 centimeter. What weight kept on pan of longer arm? A physical balance of this type of physical balance isn't possible or not. So students, there is a call. So students, as I say, and this type of physical balance is not possible, but most of the uh, yes, it is 60 and 40 centimeters. But when a particular man wants to cheat you, then only it is they uh, suppose this type of balance, but there is a wire, there is a wire, and if you stretch that particular wire in that pattern, then and this is the particular distance, so it is shift, and if you bend along this particular direction, then this is, that is the length of the balance is less amount, that then the weight is more. So distance is less, then weight is more, and if the distance is greater, the weight is less. So more paper waiters are roaming from different houses, and they uses this type of balances, we know that. So let's go to the numericals. Question number 16. Physical balance has its arm of length 60 centimeter and 40 centimeter. So this is a balanced, and 60 40. So this is 60 centimeter and this is 40 centimeter, and here it is a fulcrum. So 60 and 40 centimeter, and what weight kept on pan of longer arm? What weight kept on pan of longer arm will balance an object of weight 40 gram? What weight kept on the pan of longer arm will balance the object of weight 100 gram kept on the other pan? So other pen means the shorter arm. Here it is a weight of 100 gram force, and it is 40 centimeter. It is 40 centimeter. It is 40 centimeter. But here, suppose m gram, and this is 60 centimeter. This is 60 centimeter. So the clockwise moment is 100 into 40, and the anti-clockwise moment is m into 60. M into 60. So m equal to 100 into 40 by 60. So this cancel this one, or you can cancel this one, 2 2 ja and 2 3 ja. So 200 by 3. So 200 by 3. 200 by 3 m equal to. So 3 6 ja 18, 18, then 3 6 ja 18. Then 3 6 18, 6 6 6 6 6 6. So 66.67 approx eto gram force. So this is approx. So 66.67 gram force. If we place this amount of weight at that particular pan, then we can balance this one. So you can see that if we balance if that particular balance is used where the fulcrum is not at 50 centimeter, then if you want to sell a 100-gram force paper, then it weighs like that 66-gram force. So that paper weight cheats you an amount of approx 40-gram force, 40-gram paper. And if it is suppose 100 kg, 1 kg, then 66 kg, 40 kg paper is gone from that particular place. Okay, so this is a very vital concept that is used in principle of moments. So question number next I will try for the next day. Okay, students, so let's remain here. This is question number 13. So question number 13, the next day I will try for question number 14. Okay, let's try, you also. So thank you and welcome again to Pradeep sir classes as PSC, and this is more conceptual. Okay, thank you.